All right, here we are again, one more night. So now we can get back to our study of integrals. So let's go get everything open. So yesterday we were part of the way through 5b, and I posted 5c today, so you can look at that. I think they're both open already. Hold on. Maybe not. Hold on. This one is good. Yeah, I just want to make sure I've got the right copies of each one. And then here's C. Okay, good. So yeah, so we're going to gradually work our way up to more progressively more complicated cases and some strategies. Basically, what really separates calculating integrals from derivatives, with derivatives, you've got a bunch of rules and they're pretty straightforward. You can pretty much see in each case which one you're supposed to apply. Integrals are very different because it's not always obvious when you look at an integral which rule you're supposed to use, and in many cases you need to employ some kind of a technique for rearranging the integrals so that it fits into a form on which you can then go ahead and use one of the rules. So the challenge often is just recognizing, what should we do with this integral? You don't really run into that problem so much with derivatives. They're pretty much down to earth. It's pretty obvious what rule you're supposed to be using, but integration, it's tough. Okay, there's so many different situations you could run into, and there's often multiple strategies that will get you to the same place. So it's really a question of practicing with these more so than I think with the derivatives. Luckily, we have a friend in Symbol Lab that can help us double check our results if you're stuck. And also, with the great thing about the Symbol Lab is that you can ask it to show you the steps, and so you can go through and say, well, oh, how come this worked this way? So that's all very, very helpful to have. The idea that you can look at not just the answers, but the steps that were used to get to that point. And, like I did mention tonight, you also may have access to Mathematico, which is even more sophisticated, but it does take a while to learn how to use it. So it's there if you need it. All right, anyway, so let's get back to 5C, B rather. Oh, by the way, you know what I did? Somebody asked, and I forgot all about this. Somebody wanted to know when the next assignment was due. So I put some stuff up last night. Let me just go get onto Moodle. All right, let's log in. Okay, so what I wanted you to see is that I did put together a chapter 4 problem set. It's down here at the bottom. It's kind of mixed in here with the chapter 5 notes. And so, like as usual, I went through the book and I chose several examples that I think make sense. And so I don't think you'll have any trouble with these because we did spend a lot of time going over examples just like these. So I also posted a due date, and now I've forgotten what it was. So let's look at the announcements. Thursday the 21st. Boy, that was awfully generous of me. I guess I figure under the circumstances, since we just had a test and all, and chapter 4 is very, very long, then that would make sense. You have plenty of time to work on it. And then I'm thinking that maybe the chapter 5 problem set will be the last one because, we don't have all the time in the world. Oh, crap. Okay, it looks like I may have made a typo, and I'm so glad that you caught that. Oh, for God's sake. All right, let's investigate this real fast because I want you to have obviously the correct version. So First things first, let's go to page 377. See, now the thing is, when you search for pages, it's not exactly the same. There's a page number for the book and there's a page number for the PDF document. I find that the pages for the PDF tend to be off by about 10. So let's start with 387. So 108 would have been critical points in the domain. Okay, let me get the document open. Yeah, okay. Yeah, you can see there's a huge gap here. This is probably where the issue is right here. I don't think 337 is even in this chapter. Let's confirm that. Wow, that was bad. So here you're looking for critical points. Yeah, that looks more like it. And then over here, you're finding the local and absolute maximum minimum. Yeah, okay. So this is 377. It's obviously a dumb typo. 337. Is right here. Oh, yeah, there's no way. Okay, this is good. I'm glad you caught this. So I'm going to change it right now. And I'll save it. And I'll call this the corrected version. Ah, boy. And then I'll just post the corrected version and take away the old one. All right, that looks much better. Yeah, that should do it. So we'll go back to Moodle. Turn on the editing. Man, the net's been really slow for me the last few weeks, last few days at least. Okay, what do you? Yep. This has been going on all day. And really it's for the last several days. I don't know what it is about the summer. It just feels like the internet slows to a crawl during the summer. All right, well, we're not going to sit here and stare at this all night. I'll get it up there when it becomes available. In the meantime, we can go back and look at chapter 5b. So we were looking at evaluating definite integrals. Remember, a definite integral is the one that's evaluated over a specific interval. And so the result of that is we're going to end up with a constant rather than a formula. When we were doing the indefinite integrals, we always would end up with some kind of a function like x squared plus c or something like that. But here we're looking for a specific value because we're only evaluating this integral over a given interval, which is defined by the endpoints A and B. And so what we're learning here is techniques for solving for these definite integrals. And, ultimately what we're doing here is creating a series of rectangles and adding them up. But as you can see, if the rectangles are too large, then the approximation is not very good. So the limits, the integrals that we're using are actually the limits of what are called Riemann sums of these areas of the triangle, rectangles rather. So this is all basically background. Once we've learned this background, from now on, we can really just focus on the rules for solving for these definite integrals. Okay, it's like, any other technique. There's always a formal definition for it, but there's often rules that we can use to make things a little bit simpler for ourselves. I guess it's kind of like, what would I compare it with? Like making spaghetti by hand versus using a machine. If you're really a perfectionist, you do it by hand. You swirl up the eggs and the flour and the salt and the oil, and you roll it out and you knead it. And 20 minutes later, you have pasta dough. Whereas if you just put those same ingredients into a food processor, you'll have it in about 5 seconds. So it's kind of the same idea. But anyway, so what we were able to do is introduce some of the key properties of these definite integrals. For example, this one represents as here, if we go from A to A, no matter what the function is, that area is just 0. We see that if we reverse the limits of integration, that means that we have a negative result compared to the original result. We can add these together, we can subtract them. If we have a constant, we can factor it out. And we remind ourselves here that these symbols essentially just represent infinite sum. And so the f of x is the height of a rectangle, the dx is the width. So we did one example here. We didn't actually, well, we solved it. I kind of got ahead and showed you how these techniques actually work. In the book, this example, they just take it to about here and they let it go there. Just so you can see what you're doing with the, when you algebraically manipulate this so you can solve it. But at some point, we really do want to know the actual area under this curve. And so in order to do this, we have to go ahead and actually evaluate these integrals. First, we apply the rules. In this particular case, we were able to use the power rule in all 3 cases because this is a simple polynomial. But the interesting part is, what do you do then? So like, for example, you can see that when you have this integral based on the power rule, the integral of x cubed is, of course, let me sneak this into a new slide here. So based on the power rule, because remember how that rule works. And this again is for all n unequal to -1. If n is equal to -1, then we have a separate rule for that. That would mean we have 1 over x. And that leaves us with log absolute x plus c, if you recall. But anyway, so that means that in this result we had here, now x, when we integrate x using again the power rule, that x dx, we end up with x squared over 2 plus c. And then the third term, the integral of dx is just x. Sorry, the integral of dx is just x. Now, when you have multiple terms like this, multiple indefinite integrals, you don't need all 3 constants. It's understood that they're all different constants. And so realistically, you're going to combine them anyway into a single constant, which we don't know what it is without further information. So when you're done, you've got x to the fourth over fourth. Now remember too, you have this -3 on the outside. So you're basically going to have -3 times x to the fourth over fourth. Here you've got a 2 times x squared over 2, and this last one is 2 times x. This is the new part. Evaluating a definite integral like this means what you're doing is, let's say you have, start to keep it simple. Let's say you have x. You start out with the integral of dx. And you want to evaluate that from, let's say, 0 to 1. So when you integrate it, you're going to end up with an x, as we know. But we don't need a c here because we're evaluating this at a specific, over a specific interval. That interval happens to be 0 to 1. So the notation that we often see adopted here is this. And what this is telling me is that I'm going to evaluate this by plugging in 1 for x, and then I'll do the same thing for 0, and I will subtract. Okay, so if you had something like this, you would have x squared over 2, again, evaluated between 0 and 1. And that means you're going to have 1 squared over 2 minus 0 squared over 2. And so all you're doing is replacing the x with the 1, and then you do the same thing with the 0, and you subtract the second term from the first term. Okay, or let's say you had something like this. So here you'll have 2x cubed over 3, evaluated from 0 to 1. So you'll end up with 2 times 1 cubed over 3 minus 2 times 0 cubed over 3. Okay, so in other words, what you're actually doing more formally is you're evaluating the so-called antiderivative at x equals 1, and then you're doing the same thing for 0, and then you're subtracting 1 from the other. So in general, what you're doing is you're saying, all right, so the antiderivative, remember we designate that with a capital f of x. And so, I mean, you know, you can see this definition, but when you do it a few times and you start to realize what exactly are we doing here, we're taking the antiderivative twice and we're evaluating it first at b, then we're evaluating it at a, and then we're subtracting 1 from the other. So that's what this is all about. Okay, so this is how it's actually done in practice. You've got whatever the integral is, or antiderivative, you're evaluating it at the two endpoints here, and you're subtracting 1 from the other. And this is how you get your final result. Okay. So anyway, so here I went ahead and actually did that, and we ended up with 57/4 for this area under the curve. Now it would be, it wouldn't be fun to prove this geometrically. I don't even know how you would do that. Well, we can prove that this must work because this is what it means to define the area under a curve. We've got an infinite series of rectangles whose areas add up to 57/4. All right, now you might recall from an earlier chapter, we actually calculated one time the average value of a function over 2 points, something like this. Here's A, here's f of A, here's B, and here's f of B. And the average change between those 2 points was defined to be f of B minus f of A all over B minus A. Well, you're getting something similar here because this piece by itself is the antiderivative at B minus the antiderivative at a, valued at a, and then we're multiplying by 1 over b minus a, or it's the same thing as saying we're dividing by b minus a. So it's the same thing, except that here we're doing this with antiderivatives, as opposed to evaluating the function at those 2 points. So this could come in very handy if we need to know, let's say, if we keep increasing the output of our product, what is the average change in the value of our profits? That type of thing could come in very handy. So now here's an interesting, we're going to have a new look at this mean value theorem. And when we apply it to integrals, it gives us a very interesting result. Now, once again, if you notice, it depends on the assumption that our function is continuous. I think every result we've had in these last couple of chapters depended on continuity, but if we can satisfy that, and if we define the function over a closed interval, what this is saying is that no matter what happens, somewhere in that interval, the function reaches its average value. Okay, so let's say that this is our interval. This is point C. So the idea here is that f of C is the average value of f of x over the interval from A to B. So you can see here, well, you can't tell from looking at this particular graph, but what it's saying is that as long as the function is continuous, there has to be a point somewhere in that interval where the function reaches its average value. It's in there somewhere. Okay, and we can find it. So now we're going to use this formula again, which, remember, this is the average value of the function over that interval, expressed in terms of integrals. There's some point C such that f of C equals this average value. So in other words, they're saying that C is guaranteed to exist. Okay, now if the function was not continuous, you could get some crazy behavior like it goes directly from here to here, let's say. And then you might not ever reach the average. Like the average would be in here somewhere, but the function is discontinuous, and so therefore it doesn't ever reach that point. But once we see that there's the function is continuous, well, that means we have to reach it sooner or later. We have to get to that point. So how do we find it then? And algebraically, they make the point in the book, you could also write it like this if there's a good reason for it. They mean the same thing. All right, here we go. Here's a good example of this. So here's a nice simple example. We've got a function, it's a nice straight line over the interval 0, 4. What do you know? It's a rectangle. So somewhere in this interval, we'll find the average value of the function. And if just to get a head start on this, you could actually do this. So when x is 0, a is 0, b is 4. F of a is 8. F of b, or f of 4, is 0. So you're going to wind up with 0 minus 8 over, let's see, wait a minute. Am I doing this right? Okay. See, if A is 0, B is 4, f of A is 8. Oh, it's got a negative. Oh, that is surprising. All right, well, all right, let's just stick with the definition that we have here. We need the integral. So this is it right here. All right, so notice this is what you're trying to accomplish right here. We have f of c. See, we don't know what c is. We're looking for it, but this is the average value over that interval. And we can solve for that with our definite integral. Now, the book does it with geometry, okay, but what we could do is, since we already know how to do this, we may as well go ahead and solve for it the way, using the rules, give ourselves a head start. So this equals, okay, well, the thing is acting up. It's been one of those weeks for my technology. I'm telling you, it has been constantly frustrating me all week. I'm trying to click this thing on so I can copy it, but of course it's refusing. So I'll do it by hand. Okay, so what we can do is rewrite this. Actually, the 8 can go on the outside. We can just have 8 dx. Okay, now this first one, dx gives us just x. We'll evaluate that from 0 to 4. The second one will be 2 times x squared over 2, evaluated from 0 to 4. But you can see this is just x squared. So let's rewrite it like that. And then we can just solve. So here's what's actually happening. All right, so we have 1/4. One quarter. 8. Now, here's the important part. X evaluated over the range from 0 to 4 is 4 minus 0. And then we'll have here x squared. Okay, so in other words, remember, this was x squared, this is x. So 1/4, 32 minus 16. All right, there you go, 4. So the average value over this interval, as you can probably guess, is 4. And it should be occurring at point 2. I mean, it's pretty clear that c equals 2, but we can prove it by doing the following. We need to know f of c such that f of c equals 4. The function, the original function, f of x, was 8 minus 2x. So that means that f of c is 8 minus 2c, which equals 4. So as we expected, 2 is c. Okay, so this is what we're looking for. At x equals 2, f of x reaches its average of 4. Okay, it's right there. So this one is very obvious because it's a straight line. Okay, in many other cases, it's not going to be so obvious, but we can always use this approach to come up with the result that we need. Now here, they're giving us a graph. I found this graph to be a little confusing because of the way they drew it in here with a rectangle. I'm not sure what the point of that was, but you can see that this is in fact a triangle. The entire area under this straight line is a triangle, and you can calculate its area, but you end up with the same results. Okay, so you just have, when c is 2, f of c is 4, and this is the average value halfway down the line. Okay, now we're going to introduce, we already mentioned this the other day, something that's very important in calculus, and you can tell because of the name, it's called the fundamental theorem of calculus. Now, it actually consists of 2 parts. It's really the second part that we're interested in right now. We shouldn't neglect the first one. But it's the second one that really provides the justification for how we are solving for our definite integrals. In other words, this technique that we used up here, let's just quickly review that one more time. When you have something like this, this is a direct consequence of the fundamental theorem of calculus part 2. This is what justifies our ability to do this. And what it does, as I was saying before, is that you theoretically could continue to use the Riemann sum approach if you wanted to do that, but it's a very time-consuming process compared to simply applying our rules. And the beauty of this is that, I mean, remember, an integral or antiderivative is simply, think of it as an inverse of a derivative. So the rules that we learn for derivatives are going to come in handy here as well. So we can rely on all of these wonderful rules that we have and solve for the derivative, the integral rather, in a very straightforward way, thanks to this theorem. Okay, so I don't know if there's anybody who's responsible for this theorem. You never know. Sometimes the names of these mathematicians are lost in the midst of time. Probably there wasn't a single individual who actually created this. Let's check it out really quickly. Who invented or developed the fundamental theorem of calculus? Oh, well, what do you know? There is a name attached to it. It was first discovered by James Gregory in Scotland in 1668, and also Isaac Barrow, who was Newton's predecessor at Cambridge, but in a geometric form that concealed its computational advantage. So in other words, it was focused on the rectangles, and so it wasn't immediately obvious how much time this could save us. Well, now we know. Who's ever heard of James Gregory? I mean, he invented one of the greatest theorems in the history of calculus. Nobody knows his name. Because you know what, there was something about it, it wasn't convenient. Somebody must have come along later on and turned it into something that we're more comfortable with, and they got all the credit for it. Okay, and I'm sure that's exactly what happened. All right, well, anyway, so the first part tells us this. All right, now what's going on here? We're trying to find an integral where one of the limits of integration is actually a variable x. Now, by the way, here's an important detail with these integrals. When we integrate, the name of this variable is actually not relevant. Sometimes we change the variable name to avoid confusion with this limit. We're still integrating x, okay? We're still doing something like this. But in order to clarify what exactly we're doing, the t here is sometimes called a dummy variable. And it just, because you can see if one of the limits is itself a variable, if you had x up here and x down here, it could be very confusing. So often what we end up doing is rewriting this with a dummy variable. So don't be put off by the fact that it's a t. We're still doing the same thing. And of course, it's understood that f of x, capital F, is the antiderivative of the original function, and that implies that f prime of x equals the original function. Okay, so in other words, the way this works is that the integral of f of x dx equals the antiderivative, which implies that f prime of x is the original function. Okay, so that's what we need to remember here. We're evaluating this over a closed interval AB. And so here's a quick example of this. Okay. All right, so we're trying to figure out the integral, or the limits of integration are from a to x, 1 over t cubed plus 1 dt. Now, just because we may want to visualize what this looks like, let's go take a look at Symbolab. Our old friend Symbolab, what would we do without it? Oh, I thought I might already have it opened. So what are we looking at? 1 over. And by the way, the Symbolab doesn't care what you call the variable, xt, whatever the case may be. 1 over t cubed God, I lost it. Plus 3, I think it was. Plus 1. All right, let's take a look at the graph. Ooh, now that's interesting. So we're trying to integrate it. Wow. That's going to be interesting. But what they're basically saying here is that this is a very straightforward process because based on the fundamental theorem of calculus, the derivative of this expression is just the integral. In other words, 1 over x cubed plus 1. Okay, so we're not going to use this very often. This is important to know, but what we're really more interested in, like I said, is the fundamental theorem part 2, because this gives us the ability to do definite integrals very quickly and easily. Okay, so let's take a look at this one. So basically, I already showed this to you a little earlier. If f of x is continuous, of course, over the closed interval a to b, and f of x, capital F of x, is an antiderivative of f of x, then this relationship has to hold. In fact, let me see if I can draw a picture of this real fast. Yeah, maybe not. Okay, yeah, I don't want this to get too involved. There is a way we can draw this, but I don't want to do it right now because we have to introduce something that we don't want to do right now. So I'll tell you, let's forget the graph for now. We'll come back to this. But anyway, so now here's something, a very simple looking example. We want to evaluate this function over the interval from -2 to +2. Okay, so this is what we're trying to accomplish. And of course, in terms of geometry, I'm sure this would be an absolute nightmare. So instead, we know the rules very well. So you can see we're going to use the power rule because this is a simple polynomial. So this is now our favorite rule in the world. So of course, that means that the integral, the indefinite integral of x squared would simply be x cubed over 3 plus c. So what we're actually going to do here is evaluate that result, x cubed over 3, from the range over the range from 2 to -2. And so what you're basically doing then is calculating and what you actually are seeing here is f of b minus f of a just, oh, by the way, don't forget this is a and this is b. So therefore, we're taking f of 2 minus f of -2. And so really, all you're really doing is you're plugging in these limits of integration into wherever you see an x in the resulting integrals. In other words, whatever integral you would obtain using indefinite integration, you evaluate it as f of b minus f of a, which means you're evaluating at this value, the b, and then you're doing the same thing with a, and then you're subtracting the second one from the first one. So here you would end up with 8/3. Now, this is a tricky one because -2 cubed is -8. So you're actually going to wind up with 8/3 plus 8/3. And so altogether, we have 16/3. Okay. So let's double check this with Symbolab. Now remember, it does have this capability. Here you go. By the way, if you can't find the symbol you need for integration, over here on the left-hand side, the menus, they offer you our pre-calc and calculus. If you click on calculus, if this isn't showing, you should be able to find it there. So you've got, once again, -2 up to 2, x squared dx. Oops. And I'm sure it'll give us the exact same result, but what it will do, besides giving us the right answer, it's also going to tell us why. Okay, so in other words, we're applying the power rule to get the x cubed over 3. And this is the notation we're using. The square brackets, the b is -2, the a up here is 2. Oh, okay, they need more steps. Now, by the way, this part on the side, you probably don't have access to it unless you have a subscription. So I will show it to you. And what they're saying is, oh yeah, you've got x squared. First, this is why you have x cubed over 3 because of the power rule. But then how did you come up with this final result? Well, they didn't really ever quite get around. I don't think they did a very good job here, but they did exactly what you see here. And then here's the resulting graph. And so they very kindly filled in the area that we were looking for. Interesting. I never saw that before. I guess whenever we've been looking for the integration, we were so interested in the result, we never actually looked at the graphs. And look at that. That's a nice graph. But yes, this is exactly what we're looking for. All right. Well, let's try another one. Now, this one is a little bit messier, but still, as you can see, it is a simple polynomial, which means the first thing we should probably do is rewrite it a little. And then just a quick reminder, because of the power rule, this would give us x to the 5th over 5 plus c. This would give us x to the 4th over 4. Let's make that a little neater. So what we're going to wind up with, as you can see in the next page, is the x to the 5th over 5, but now evaluated between 0 and 3. And then we also have the second term, 3 times x to the 4th over 4, again evaluated from 0 to 3. So what are we actually doing here? So this is a little bit messier because you've got to evaluate within each set of brackets. So I'm replacing the x's with the 3 first and then the 0 for each term. And then it's just a question of cleaning it up a little bit. For example, 3 to the 5th. Oh, God, I don't have that one memorized. Hold on one second. Uh, 243. And of course, I don't have to worry about this. I'm just subtracting 0. Same thing over here. 3 to the 4th would therefore be 81. And now it's just a question of simplifying the fractions and finding a common denominator. So probably what you should do is multiply this one by 4/4. And this one by 5/5. All right, so 486 times 4 is 1944. Plus 243 times 5. $12.15. Okay, wow, what a mess. Okay, so I hope I haven't made any dumb mistakes. I've got 3159 over 20. No, that was it. Okay, perfect. So yeah, here, I mean, I typed them all out. I just wanted to see exactly what I was doing. So it's 3159 over 20. It's approximately 160. Okay, so, but you notice the technique is exactly the same. Well, what have we actually done here? We evaluated this integral the normal way. In other words, we use the power rule, but the new part is the evaluation. And so you're always evaluating within each term by applying the function, the top level, this is the b, the so-called b, and that's the a, and you're evaluating them with those 2 points and subtracting one from the other. Okay. Now here's an interesting one, because all of a sudden we don't have a regular polynomial, we have 3e to the x. You might remember from way back, one of the many rules that we learned with indefinite integrals is that this is very simply e to the x plus c. So for here, we should probably rewrite it like this. And then you can see we can apply that rule right here. So we'll just end up with 3e to the x. Now, we don't need the constant, but what we do need is to evaluate this whole thing 0 to 1. So we have 3e to the 1 minus 3e to the 0, 3e minus 3, or 3 times e minus 1. So let's have Symbolab. Now, of course, Symbolab can not only do the calculations, but it can do the graph, which is a very big feature. Let's try that. I'm dying to see what it looks like. I'll start it all over again. It's been my experience with Symbolab that once you start to mess up something, it's hard to fix it. You might as well just start all over again. So it is what we predicted, 3 times e minus 1. And let's see what the graph looks like. Oh, wow, very interesting. Because remember, e to the x rate increases very quickly. So this is what the area is that we're looking at. Okay. All right, what other goodies do we have up our sleeves here? Oh, now this one might, I think I mentioned this a little earlier. This is one of those special cases. Hold on 1 second. Yeah. Okay. Okay, yeah, that was that case. This is actually, remember, because x, 1 over x is simply x to the minus 1. This is the special case that the power rule doesn't apply to. So we always have to remind ourselves it's not equal to -1. Here it does equal -1. So we have a separate rule. So this thing is going to be equal to log x. Now we don't need the constant, but we're going to evaluate this between 1 and 3. So we'll have the log of 3 minus the log of 1. The absolute values we don't need because these are both positive constants. And also don't forget, no matter what the base is, the log of any number, the log of 1, no matter what the base is always 0. Okay, so we end up with just log 3. All right, what the heck? Let's do it on Symbolab. 1 over x from 1 to 3. So it is log 3. But let's take a look at the graph. Yeah, okay. And that's what we're looking for. Excellent. Now, you know, it's interesting. I always see this. It says view interactive graph. I'm not quite sure what they're talking about there. What exactly does that let us do? I think one thing it will let you do is add more functions onto the same graph. But beyond that, I'm not sure what other capabilities we have. I guess we could add labels and make it smaller or bigger. I don't know what other capabilities it has. All right, well, anyway. Now, here's one that you might not be happy to see because it involves trigonometry. Trigonometry is not necessarily anyone's favorite topic, but we need to be comfortable with trig functions too. So if you recall, one of the rules that we saw is that the integral, well, actually, let's even take a step further back. So when we integrate this, it stands to reason that we're going to wind up with negative cosine x. So, you know, sometimes you can memorize these rules, but sometimes you can reason them out. If you remember the derivatives, you're basically, remember, just working it backwards. So if the derivative of cosine x is negative sine, the integral of just plain sine would be cosine x, but because, I'm sorry, negative sine would be cosine. We don't have that. So we end up instead with negative cosine x. So we can rewrite this now. So you've got negative cosine pi minus a minus cosine 0. You got to watch it with those negatives. So the cosine of pi actually turns out to be -1. So we have -1 plus 1. So you actually end up with 2. All right, so let's see what this looks like on a graph. Here we are. So we have 0 to pi. And this is just sine x. So it is 2. And, oh, look at that. Yeah, that looks right, because the sine of x, if you look at the graph of sine of x, just plain sine of x, it goes up and down like a roller coaster. What we just caught was part of the roller coaster there. Yeah, exactly. It looks like this. So we're focusing our attention between 0 and pi. And there's essentially one cycle. All right. So those are all examples. They're meant for practice. We want to be we want to get comfortable calculating definite integrals using this second part of the fundamental theorem of calculus. But remember, I mean, it's really just the same thing as the indefinite integrals, except for the part where we are actually evaluating it. And that part is very simple as well. So they're really not that much more difficult. No, in fact, they're not really difficult at all. So anyway, so what's coming up in part C is that we're going to see some more complicated cases. So where we may need some strategies to help us obtain an integral where we can actually use the rules. And in some cases, the strategies are fairly complicated. So I think because it's a few minutes after 8, let's stop right here and have our break. And then we'll dive into these, obviously more difficult integration formulas where we really have to start thinking in terms of how to take this expression and make it workable using the rules that we know. And, there's certain strategies that we can use on a regular basis. But in some cases, we really, the techniques that we use will be pretty unique to that particular situation. So we'll start out with some basic cases, but in each of these cases, we're going to need to not necessarily use the original integral. We'll probably have to make some changes to it. Either that or we have to approach it in a slightly different way. In particular, when the chain rule gets involved, that really does make things a lot more complicated. So, all right, we'll see how that works in a few minutes. All right, so it's time for some more complicated antiderivatives or integrals. So let's start with this one. Now you look at it and say, oh my God, what's going on here? We have a product of some kind here, and we haven't seen any rules that help us deal with something like that. But what we can do is at least attempt to see what happens if we simply multiply this out. And if that doesn't work, the thing about these integral problems is that if you try a strategy that doesn't work, well, you can always try something else. So let's just do that. Radical x, it's radical x dx. Now, in a case like this, you're much better off, in my opinion, using the exponents rather than the radicals. So you'll have x to the 1/2. This means you're multiplying x to the 1/2 times x to the 1st. So this is x to the 3/2 power. Now, once you've got it in this form, it should be pretty clear that all of a sudden we can apply the power rule to both of those terms. So we've rescued what appeared to be at first glance an impossible to solve integral, or at least one that would be very difficult without learning more rules. So in this case, we didn't have to do anything more complicated than simply rewrite it algebraically. All right, so that means you've got so what you can do is break it up into two integrals and add them together. And now we can apply our favorite rule of all time, the power rule. So you're going to have, in this first case, x to the 3/2 over 3/2 evaluated from 1 to 4. And here you'll have x to the 5/2 over 5/2 evaluated from 1 to 4. So why don't we simplify this a little? It's kind of awkward to be dividing by a ratio like that, so we'll rewrite it. So remember, when you divide by 3/2, it's the same thing as multiplying by the inverse of the 3/2, which is 2/3. And now here we do the same thing. So now it's just a question of plugging in the 4 and the 1. Okay, so let's do that. So just quickly remind you that we have 2/3 x to the 3/2 from 1 to 4. 2/5 x to the 5/2 from 1 to 4. So now we can just take 2/3 4 to the 3/2 power. The 2/3 applies to both, so we can just write it like this: 2/3 times 4 to the 3/2 power. Or actually, no, I'll tell you what, let's just keep it simple. Let's do this. We'll write it like this: 2/3 4 to the 3/2 minus 2/3 1 to the 3/2 is the first term. And the second term will be 2/5 4 to the 5/2 power minus 2/5 1 to the 5/2 power. Well, now, luckily, in each case, 1 raised to any power is just 1, so that's easy. But what about 4 raised to the 3/2 power for something like that? Just a quick reminder what that means. what you're actually doing here is taking the square root of 4 and then raising that to the third power. So you've actually got 2 cubed, which is 8. And over here, we've got 4 raised to the 5/2 power. So you're taking the square root of 4 and then raising that to the 5th power. So you've got 32. So what you've actually got here is 2/3 times 8 minus 2/3 times 1 plus 2/5 times 32 minus 2/5 times 1. All right, well, it looks like a mess, and it kind of is. So let's insert a new slide here. So we'll have 16/3 minus 2/3 plus 64/5 minus 2/5. Now, of course, we need a common denominator. We might as well use 15. All right, so we'll have 70/15 plus 182/15. So if I haven't made any algebraic errors, that should be it. No, something's not right. Ugh. There's one mistake in there somewhere. All right, let's figure it out. You know what I'm going to do? Let me just double check one thing. Four to the 3/2 power. I'm going to double check that. That's fine. 4 to the 5/2 power. That's fine. All right, so we have 16/3 minus 2/3 over here. On the right-hand side, 64/5 minus 2/5. Huh. Oh, God, it's so simple. Look where I made the mistake. The easiest part, well, of course, that's always how it works, isn't it? Yeah, so that's it. All right, so what did we do here? So that really, except for this part where we had to decide what to do to get this into a more usable form, we just multiply the radical x by both terms in the parentheses. The rest of it is exactly what we've been doing. We applied the power rule to each term to come up with an integral. And since it's a definite integral, we evaluated each one from 1 to 4, and then we combined them to come up with our final result. Good. Okay. So I did all the steps here. I just wanted you to see where they came from. Now, the net change theorem, we'll just briefly introduce this. It basically just gives us a way of rewriting integrals in a convenient way. So the net change theorem shows that when a quantity changes, the new value of whatever the variable is equals the original value plus the integral of the rate of change. So this is where integrals come in useful in real world applications. So in other words, this implies the following two expressions. So we're going to see an example in a second. And we can use either one of these expressions to come up with our result. Remember what we're looking for, though, is the change. What did the variable change to? In other words, what was its original value? What is it now? So here's a good example. This is a real world example. And it's actually a physics example. We start out by turning on an engine at time t equals 0, where t is the number of hours that have elapsed. And the rate of consumption of the gasoline is 5 minus T cubed for the first hour. How much gas do we use up during that hour? Now, you might think, well, that's going to be hard to calculate. But since we're looking at the first hour, what we're basically doing is we're integrating that function over the interval from 0 to 1. Because what we're trying to do, and by the way, let's go look at the graph for a second. 5 minus T cubed. Oops. So we're looking for, let me take a picture of this. I obviously can't write on the screen there like that. Oops. Okay, so we're looking for the interval between 0 and 1. This would be 1 right here. So this is showing us the gas consumption. And so this one is a very straightforward integral. We break it up into two pieces. We have 5 dt here, we have minus T cubed. And of course, using the power rule, we end up with T to the 4th over 4 with the indefinite integral, T to the 4th over 4 plus C. But here we're evaluating it from 0 to 1. The integral of dt is simply T plus C. So we've got T over here, right there. Okay, and then the T cubed became T to the 4th over 4. So now evaluating this one is very straightforward because the two numbers are 0 and 1. The two limits of integration are 0 and 1. So this is a very simple case. Let me copy this into the next slide so we can refresh our memories. And so what have we done? So the first term, we just have 1 minus 0 because we're substituting 1 and 0 into the t. Here, it's a little trickier. Remember, we have a negative here. And so we've got 1 to the 4th power over 4 minus 0 over 4. Technically, it's 0 to the 4th power over 4. So you have, in the first case, 5. In the second case, you're subtracting 1/4. And our final result is 19 over 4. Okay, so in other words, this shaded region, the amount of gas is 19 quarts gallons. All right. Now, we're going to take our minds back a little further. At one point, we introduced the concept of even and odd functions. What does it mean to be odd? And what does it mean to be even? Well, with an even function, f of negative x equals x for all x in the domain. Classic example, y equals x squared. So let's say that f of 2 is 4. What they're trying to get at here is that it's symmetrical on either side of the vertical axis. Okay, so this is y equals x squared. It is defined to be an even function. And it's characterized by being symmetrical Now, odd is this one, f of negative x equals negative x for all x in the domain. And so y equals x cubed is the classic example of an odd function. And, we've seen this so many times before. The symmetry is defined to be with respect to the origin. So it's basically, what you're effectively doing is saying, this is a mirror image of this. If you can imagine flipping it upside down, and then I guess, you're sort of looking at it in the lake, but you're flipping it over as well. Those are the two sides that are equal to each other. Now, what does this have to do with anything? Well, if we have an even function, we can integrate it in a very interesting way. And the same thing actually holds for an odd function. So what they're telling us is this. As long as the function is continuous and even, and you notice the limits of integration, one is simply the negative of the other. So this could be -3 and +3. What we can do is integrate from 0 to a and then simply double that amount because these two are equal to each other. Okay, in other words, what we have here is -a to 0. And what we have here is 0 to a. So basically what it's saying is don't bother doing them each separately. All you have to do is this one and then double it and you're all set. Now that may or may not be the most useful result in the world, but it's good to know that it works this way. Now with an odd function though, here's what happens. If you're doing something like this, here's a, and here's -a. Those two will add up to 0 because one is the negative of the other. Okay, so you have f of -a to 0. Let me try that again, 0. I'm sorry, let me try that one more time. -a up to 0, we're integrating it. And then here we have 0 to +a. And because in the first case, the entire area is under the horizontal axis, and in the second case, it is above, and they are mirror images of each other by definition of it being an odd function, that means they exactly cancel each other out. And so the entire integral from negative to +a is guaranteed to be 0. So these are kind of helpful results to have. Sometimes this can help us maybe come to a result sooner than we might otherwise. Or, you can think of it as a special case that can maybe save us a little calculation time. So here's a good example of this. Okay, now it's not always obvious by looking at these functions. You can prove formally whether it's even or odd or neither, but let me show you what the graph looks like. And you'll say, oh my God, yes, it's so obviously an even function. Because everything to the right of the y-axis exactly matches what's on the left side. So that we already know that. And so if you notice also, if you think of a as 2 and -a is -2, the results that we just saw showed that this could be rewritten as this. So in other words, we can just focus on the right-hand side. Because we know they're equal to each other. And all we really need is the total area is 2 times the area on the right. All right, so let's prove it. Okay, so we can easily break this up into two separate integrals. We'll rewrite this as 3 times the integral of x to the 8 dx minus 2 dx. Now, of course, recall that by the power rule, this is going to give us and again, by the power rule, this will simply give us x plus c. All right, so you can see we've done exactly that, but we have to evaluate them now from -2 to 2. Okay, so this one will be so again, you're evaluating this when x equals 2, then you're doing the same thing for -2 and subtracting. Okay, now we just have to evaluate it. Now it's a bit of a mess, of course, because we'll have some fractions, but actually turns out pretty well. 2 to the 9th turns out to be 512, by the way. So we have here 512 over 9 minus a minus 512 over 9. Over here we have -2 minus -2. So if you're careful with this thing, you've got 3 times 1024 over 9 minus 8. If you rewrite this as 70 seconds, actually no, just ninths. All we need is ninths. Ultimately, you end up with 3,000 over 9. And that gives us 1,000 over 3. So here we did it the normal way. If you notice, we didn't take advantage of that property. Remember before we said that we should be able to, under these conditions, rewrite this as 2 times the integral from 2 to 0, 0 to 2 rather, of 3x to the 8th minus 2 dx. So we're going to do that now. We're going to try it the second way and confirm that our result works. Okay, so because this is an even function, this should give us the same result. So let's do it. So you've got this original integral. I'm doubling it, but I'm only going from 0 to 2. And so I bring the 2 outside here, and I evaluate these the same way we did before. But remember, interval, the ranges over which we're integrating are from 0 to 2 now instead of -2 to 2. So now I substitute, and well, you can see if you work through all the algebra that you will in fact end up with 3,000 over 9. Same thing. Oh, I didn't reduce it to 1,000 over 3, but of course it's the same thing. Now, the book has a graph here, and I was looking at it, and I was thinking, I'm not really sure what they did here. Because yes, on the left, we have this standard approach to calculating the integral between 2 and -2, but I don't know what this is supposed to represent. The theory is basically just saying that you can just take this and double it and end up with the same area under that curve. I'm not sure what that part B is even supposed to tell us, so we'll kind of gloss over that one. But on the left, you can see that clearly the 2 blue areas are equal to each other because of the symmetry. Well, now we're going to have to take a crack at our odd function. And so let's try -5 sine x dx integrated between negative and positive pi. And again, it's hard to tell by looking at a function like this if it's even or odd. We can prove it algebraically, but the graph kind of says it all. This is an odd function because this one, the blue section over here, we'll call it 1, is an exact match for 2. They're the same, but they're in opposite quadrants, I guess you could call them. So we have an odd function, which means in principle, if I add together these two sections, they should give me a 0. Well, let's prove it. Okay, so we'll integrate over the entire range from negative to positive pi. And we just saw this example a little bit earlier. The integral of sine x is equal to negative cosine x dx. So we're going to evaluate this, oh, sorry, not dx, plus c. And so we'll, since this is a definite integral, we'll instead be evaluating -5, which I moved to the outside, times negative cosine x, integrated over the range from negative to positive pi, which you can see here. I've, in the parentheses, negative cosine positive pi minus negative, or minus cosine negative pi. Now, it turns out that the cosine of pi is -1. All right, let's go look at Symbolab. So yeah, -1 for pi. The cosine of negative pi is -1. Okay, so when you plug in all those numbers, ultimately you'll end up with a 2. Okay, now here's going to be the fun part. Why don't we, oh, wait a minute, am I looking at the right one? Sorry, I think, hold on a second, did I lose my place? No, I did it. It's fine. We're good. I thought I lost my place here. No, this is it. I just wrote it by hand, and then you can see the final result is here. But I think it's a good idea to look at the graph that will be produced by. Oh, yeah, I know what's going on here. We have to show that the two pieces would add up to 0. So let's take a look at the graph in Symbolab. Wait a minute, what did I do? Did I do something wrong? No, I was in the wrong place. Okay, no, I got confused for a second. So it's 0. It is 0 as we predicted, but let's take a look at the picture and prove it. Let's go back to Symbolab. We have 0 to pi sine x dx. So no, I did it again. I'm going to have to turn this one off. I'm going to keep doing this over and over again. This is what I wanted. Yeah, no wonder. Okay, -5 sine x dx, but ranging from negative to positive pi. This is what we wanted. There we go. Now we should see something interesting. Oh, now what happened? All right, obviously I did something wrong. Let's try that again. Minus pi up to pi, -5 sine x dx. All right, let's try that one more time. So it is 0, but this is why. You can see the two shaded regions do in fact exactly offset each other, which we could have predicted because this is an odd function. And the limits or the range of integration is between negative and positive pi because those are equal to each other except for the sign. That means that the two will exactly offset each other. All right, now we're ready for some really heavy duty techniques. This next one is really useful, but it does take some getting used to. Basically, we use this when the chain rule has been used to derive the integral that we need to study. How does this thing work? Well, here's the theoretical reasoning behind it, but I think the best way to learn the substitution method is to simply use it. So let's do an example. What exactly are we trying to do here? When we look at an integral, let's say it could be anything. Let's say it's x squared plus 3 dx. Oh, actually, no, that's a nice one. Let's try something different. Okay, now that looks on the surface to be a very difficult integral because there's multiplication involved. Now, we certainly could, in this case, multiply this out. And we can then apply the power rule. But this time we're going to try something different because it illustrates this very powerful technique called the method of substitution. And so here's what the logic is behind it. If we look inside this integral, we're looking for a function such that we can write it as g of x equals u. And so what we want is our integral to go from this to something like this, some function of u to the du times du. So in this case, how would that work? So let's rewrite it the way it was originally. And we're only going to have time to just barely start this. In fact, this is such a complicated topic. I don't want to rush through it at all. Let's try this. What if I were to let u be a function of x? Wait a minute, what did I do here? Oh, okay, no, you know what I just realized? I made a mistake here. I wanted to do something a little different. Yeah, this one would have been easy, but what if we had something like this? Instead of that, let's try this. Now we've got a mess in our hands. Now we really do need to use the method of substitution. So let's try that. So u will be whatever's going on inside the parentheses here. And then the derivative of u with respect to x would be 2x. Okay. Now, how does that help us? Because then du would be 2x dx. So what we're basically doing is changing the variable from x to u, and then later on we'll switch it back. So in other words, we're basically replacing this with something more convenient. And so what that means now is that this thing is actually equal to u cubed. Because remember, we define u to be x squared plus 3, u cubed. All of this is du. And so now we can apply the power rule. So we end up with, and by the way, here we're using an indefinite integral, so we do need the constant. But now we're not done because we need to replace the u with x squared plus 3. And we're done. Ooh, wow, that was interesting. And if you apply the chain rule here, see now you can always check the results with integrals by taking their derivatives. So if your original function had been This result we just got x squared plus 3 to the 4th power over 4. We don't have to worry about the constant because its derivative is 0. Using the chain rule, f prime of x will be 1/4 from here. And then this piece by itself will have a derivative of 4 x squared plus 3. We subtract 1 from the exponent, and then we multiply by the derivative of what's inside the parentheses. So these cancel out, and we end up with x squared plus 3 cubed times 2x. So before, when we were integrating this function, it looked like this. So this proves that we did this correctly, okay? Because the integral we obtained here, once we differentiate it, it brings us back to the original function that we were integrating. So the key to the whole thing is to find some part of this integral and call it u, and then make sure that you have the correct value for du dx. If you do, you're all set. And then you can apply the power rule to u instead of x. And you basically are replacing a very messy expression with one that's not so bad. And then you replace the u with x and you're all set. So like I said, this is a very complex idea. I didn't want to rush through it. I just want to introduce it to you so that what we can do now is we can do several examples of this on Thursday. And once we've done it 5 or 10 times, you'll see that after a while, you start to get pretty good at this. But for very complicated cases, sometimes the choice of u is not always obvious. That's where it can get a bit sticky. The good thing, though, is that if you pick the wrong thing for u, you can just try something else until you find the one that works. But after a while, you start to notice there's certain patterns that form, and you'll start to notice, this is probably what we should do for our u, and you'll get pretty good at it. Let's put it that way. So what we're doing here is called the method of substitution. And we're specifically applying it here to indefinite integrals. Later on, we'll apply it to definite integrals as well. But the point of it is that, well, yes, we could have expanded this and turned it into a set of, a very messy polynomial. It's not necessarily worth all that trouble because this approach is a little bit simpler as long as we really choose the right value of u. So in some cases, you'll find that really this is the only option you have because the expression is such a mess, you can't really do anything else with it. So here it's sort of optional, but there will come cases where really it's the only way you can find the integral. Anyway, so we'll discuss all that on Thursday. So I don't want to overdo it here, but yes, we're going to go through and do a bunch of these cases and then like enough so that we can get really good at this. And so after a while, it'll become second nature to recognize a method of substitution problem. So, all right, I guess we better knock it off here before your heads explode. So we'll do this some more on Thursday. All right, so see you all then. All right, good night.